Okay, so the point of this recitation is to give you a guided walkthrough of how to approach and answer correctly an exam. So the exam we're going to talk about is the last exam 2 that was offered. So summer 2019, Organic 2, exam 2. Obviously the first part is just true or false. So in the true or false question, besides just looking up the correct fact, it's important that you understand what is the point of each question. So for example, question 1, primary amine plus ketone equals imine plus H2O is an example of a condensation reaction. The important thing there is that you know what a condensation reaction is. You should also think about how the question can be asked in another way. If you know that that's true because it's a condensation reaction, you have to know the definition. Because what about if I said that transformation is a substitution or that transformation is an elimination? So that's really a question that's testing your knowledge of class of reactions. Question 2, ketones can be reduced to alkanes, functional group into conversion. These functional group into conversion questions are now easy because you can now just look at your summary chart. So bottom of your chapter 18 is reduction. In fact, that's a deoxygenation. Next, question 3. Nitriles are stronger bases than primary amines. So this is a base strength question. So you then look at the top part of the summary for chapter 19. That talks about your base strength. All substituted amines stronger than ammonia. That's irrelevant. Then you've got the resonance aspect. This is irrelevant. This question is dealing with nitriles and amines, which comes down to a difference of hybridization. The reason why that's false is that the nitrogen in the amine is sp3, nitrile sp. So if a question is false, it's also going to be beneficial for you to know why it's false and how you could make it true. Question 4, thionyl chloride has the formula SO2Cl. Again, now you can just look in your reagent sheet and see that thionyl chloride does not have that formula. You should look to see what that formula is. Of course, I was being devious and put one that's very similar, but again, this is to show you or encourage you to pay attention to detail. Question 5, silver mirror test is a way to detect primary amines. That's false. You should know what that test does. You look in your notes, there's a chemical test that produces a silver mirror and that detects aldehydes. Question 6, NaBH4 is a good proton donor. That's false because NaBH4 along with LiAlH4 are hydride donors. Hydride is H minus, a proton is H plus. Those two things completely different. Aldehydes, next one, aldehydes more sterically hindered than ketones. That's false. You know that from their structure, from their different structural motif, and that also ties into their relative reactivity. Obviously, aldehydes more reactive than ketones. Question 8, aldehydes are produced by careful oxidation of carboxylic acids. Again, this is a slightly devious question, but it's false because there is a connection between aldehydes and carboxylic acids, but you don't oxidize a carboxylic acid to get an aldehyde. You have to oxidize an aldehyde to get a carboxylic acid. Question 9, amines are bases and can be protonated to produce ammonium salts. That's kind of the main function of amines. Question 10, talking about chirality. Obviously, that's true. So then if we look at question 11, predictable question, functional groups. So functional group name and functional group structure. Have to know them. If they're in chapter 18 or chapter 19, you have to know them. Question 12 is just checking that you can draw a correct Lewis structure, including non-bonding pairs for those functional groups. Question 13, standard IUPAC question. So molecule on the left, you would tackle this by asking yourself what functional groups are present. Obviously, you can see a ketone in the left-hand side molecule. Really, the ketone is the only functional group there. You have a cyclic ring also. So you're going to name it as a ketone. You're going to look for the longest sequence of carbon atoms that includes that ketone, which is 7. So it's some type of heptanone. Those 7 carbons are in a ring, so it's a cycloheptanone. You also have 2 substituents on that ring. For a cyclic ketone, the ketone establishes carbon number 1. Therefore, you would number around your ring starting at the carbon-al-carbon of the ketone, giving your substituents as low number as possible. So that's why it's a 3,4-dimethyl cycloheptanone. Then there is an issue of relative stereochemistry. For the 2 methyl substituents, they are cis to one another. If you want to be more precise, the carbons connected to those methyl groups are actually chiral. So I assigned the absolute stereochemistry of those. You would get a bonus point if you put the exact chirality of each of those chiral centers. Right-hand side molecule, you look at the functional groups. The only functional group present there is an amine. It's a primary amine, so you look for the longest sequence of carbon atoms to which the nitrogen is connected. That longest sequence is 4, so it's some type of butanamine. That nitrogen is connected to carbon number 1. You number your main chain so as to give the nitrogen substituent position as low number as possible. When you do that, you see that you have a methyl substituent. That methyl substituent's on carbon 3, so that's 3-methyl butan 1-amine. Question 14 is again another name structure question. This is dealing with one of those exotic or trivial name of a nitrogen containing species. So this is testing that you understand what aniline is. So chapter 19 has a bunch of different compounds that include nitrogen. So for example, pyrrole, pyridine, aziridines. If it's in the notes, I would say you have to know them, but now I can say if it's in the notes, you have to be able to find them. So you have to be able to find aniline, draw that structure, understand that it's a diethyl aniline, but the prefix NN is telling you where those 2 ethyl substituents are located. Question 15 is give the reagents to generate the following products. So the key to these questions is functional group interconversion. You look at your start material, you look at your product. What is that functional group interconversion? Identify that, then find it in your summary chart, and that will tell you the reagent. So when I look at question 15a, it's a alkyne, in fact a terminal alkyne, being converted into an aldehyde, pentanal. So terminal alkyne to aldehyde. So you look in your aldehydes and ketone sheet, terminal alkyne to aldehyde, dialkyl borane, H2O2, NaOH. So now, if you have access to your summary charts, it's now just an issue of functional group interconversions. 15b is ketone to alkane. So now, bottom of that chart, this is one of those deoxygenations. 3 different ways to do that. 15c is a primary amine being converted into an amide. So amine to amide, you can find in the chapter 19 summary, second box, part 2, acylation. So amine to amide is achieved with an acid chloride. You might say, well, what acid chloride do I use? You can see that the relationship between the amine and the amide is that you've then added a 3-carbon substituent onto that nitrogen. Therefore, you use a 3-carbon acid chloride. Part D, functional group there conversion is nitrile to ketone. So looking at aldehydes and ketones summary, bottom of box 1, nitrile to ketone is Grignard followed by H3O+. You say, well, what Grignard do I need? The carbon of your nitrile, which becomes the carbon of your ketone, is now connected to a CH3 substituent. Therefore, you need the CH3 version of a Grignard, CH3MgBr. Part E, the functional group interconversion here is carboxylic acid to aldehyde. So you look in the middle of your aldehydes and ketones chart, and you see carboxylic acid, and you see aldehyde. And you see that you cannot go directly from carboxylic acid to aldehyde, but you have to go from carboxylic acid to acid chloride, then to aldehyde. So again, reagent set E, which is your thionyl chloride, correct formula, and then acid chloride to aldehyde is your modified reducing agent. So lithium aluminum tri-T-butoxyhydride. Question 16, mechanism question. We said that aldehydes and ketones only undergo two reactions, nucleophilic addition and condensation. This is nucleophilic addition. If I give you the intermediates, mechanism questions are easy because all you have to do is account for what bonds have been formed and what bonds are broken. So in our first part, the RMG covalent bond exists, but in our second set of intermediates, R is no longer bonded to Mg. That bond is broken. Those two electrons must have moved somewhere. The R group is now connected to the carbon that was the carbon of the CO double bond. So you can tell that those two electrons moved from the RMG bond to the carbon. The pi bond of the carbonyl has moved onto the oxygen. That explains why it has the negative charge. Then our alkoxide intermediate is transformed into our product with an OH. So we have to make an OH bond. Need two electrons. We need to use one of the lone pairs on the negatively charged oxygen to make the bond to the hydrogen. H3O plus becomes H2O. The positive charge has been neutralized. The oxygen goes from bound to 3 hydrogens to bound to 2 in H2O. Therefore, the electrons must move onto the oxygen. Question 17 is just a base strength question. So we have ammonia, ethanamine, that's a primary amine, and NH4+. Strongest base question is which two electrons are most easily donated. So NH4+ has no lone pairs. That cannot act as a base. So now it's just a question of ammonia versus ethanamine. So in our base strength box in the top of chapter 19 summary, primary amines are a stronger base than ammonia. For that reason, ethanamine is the strongest base. Part B, we've got pyridine, pyrrole, and then a cyclic secondary amine. So none of these are ammonia. So we then think about, are any of the lone pairs in 17b stabilized by conjugation? Are any of them stabilized by aromaticity? So the nitrogen in pyridine is not involved in the aromatic system, so no conjugation there. But the lone pair in pyrrole is involved in conjugation. That's essential for the aromaticity. So the lone pair on pyrrole is tied up in aromaticity. That's unavailable for donation. The lone pair on the nitrogen on the right-hand side molecule is not involved in conjugation. So of those three, the weakest base is pyrrole, because that's involved in resonance stabilization. So now we have to decide between the ring on the left and the ring on the right. Neither of those nitrogens have their lone pair tied up in conjugation. So next consideration is hybridization. Hybridization of the nitrogen in pyridine is sp2. Hybridization of the nitrogen in the ring on the right is sp3. Your base strength summary says sp3 hybridized nitrogens are more basic than sp2, therefore molecule on the right. Question 18, another mechanism question where again I gave you the intermediates, so all you have to do, so this is now for the second half of a condensation mechanism, curly arrows have to describe the movement of electrons that create new bonds or destroy existing bonds. So in the first step of that mechanism, you see that hydrogen is no longer bound, covalently bound to X. Those two electrons have to move. But the oxygen of the hemiacetal ends up getting a new hydrogen connected to it. So again, this is showing you which electrons move because you have to connect or disconnect atoms. Question 19, a question that really sort of makes you think. Again, this comes down to functional group interconversions. So if we look at 19 part A, benzene to that tribromobenzene. Now initially, you might think this could be straightforward because you know how to put a bromine onto an aromatic ring. That's Br2 FeBr3, classic EAS. However, you would then realize that a bromine is in fact an ortho-para-director for EAS. And that means once you've put one bromine on, the second bromine would go ortho or para to that. And that's a problem because all three of those bromines are meta to each other. So that's what makes this question slightly more challenging. However, in chapter 19, we talk about the exploitation of using the NH2, which is a very strong directing group. And that NH2 can direct ortho-para relative to itself. And so in my answers, I've drawn that if you take aniline and brominate it, it will then give you the tribromo version with the bromines in the correct orientation. However, we've then got to get rid of that NH2, and so we can use some of our diazonium chemistry to then get rid of the NH2 and replace that with a hydrogen. So with part B, we're going from cyclobutanol to some type of alkene. To answer this question, you'd say, what ways have I seen to generate alkenes, especially generating alkenes that have additional carbons relative to my starting material? The only way that you've seen how to do that is the Wittig reaction. Then you'd say, or look at your notes and say, well, the Wittig reaction requires an aldehyde or ketone. Obviously, my starting material is a secondary alcohol. That requires you then to make the connection that you can convert a secondary alcohol into a ketone. So that's oxidation. Then you get to do the appropriate Wittig chemistry, get your product. So again, what this is testing is your ability to relate functional groups to one another. So part B there is not how do you go from A to B, it's really how do you go from A to C, but you have to know what that intermediate B is. So that intermediate B has to be something you can convert the secondary alcohol into, and also something that you can convert that B into an alkene. So the ketone is the only one that fits both of those criteria. Chapter 20, to be honest, chapter 20 is the question that normally gives people the most difficulty. So this is how you address it. So it's about functional group interconversions. Look at your starter material. Your starter material in the middle of this wheel of easy points contains an aldehyde and a ketone. So we're just going to use aldehyde and ketone chemistry to solve this problem. If we look at the start material and then the arrow that moves to the left, functional group conversion is aldehyde has become primary alcohol. Ketone has stayed as ketone. So you then look at your aldehydes and ketones summary and say, well, how do I go from aldehyde to primary alcohol? That's hydride reduction. But then you need to be mindful and say, well, I know that that reagent also would react with my ketone. Is that going to be a problem? Fortunately, your notes allow you to be an expert in this and say, well, I know aldehydes are more reactive than ketones. So by adding just one equivalent of my hydride reducing agent, it does the aldehyde, doesn't react with the ketone. If we look at the vertical arrow going down, this is really testing the same thing. We have aldehyde and ketone in our start material. Reagent is primary amine. So primary amine, an acid with an aldehyde, gives you an imine. Also, that same reaction is possible with a ketone. However, aldehyde's more reactive than ketones, so it's the aldehyde that reacts and therefore forms the corresponding imine. If we look at the transformation going with the arrow to the right, again, start material is aldehyde and ketone. Here we're using excess lithium aluminum hydride. So hydride reacts with aldehyde to give primary alcohol. Lithium aluminum hydride reacts with ketone to give secondary alcohol. Both of those are possible. Excess reagent allows both of those transformations to occur. Really, the most difficult question or answer in this problem is the arrow that goes vertically up. Start material is aldehyde and ketone. Product functional group is aldehyde and tertiary alcohol. So the conversion here is ketone to tertiary alcohol. And initially you might say, well, middle of chapter 18 summary, ketone to tertiary alcohol reagent F in the red is Grignard followed by H3O+. That's true, but the problem here is if you use that Grignard reagent on that start material, aldehydes are more reactive than ketones, the aldehyde would react first. For your vertical arrow going up, you want the ketone to react. So this is a problem of relative reactivity. You can't just add the reagent because it's going to react at the aldehyde, not the ketone. The solution to this is to use a protecting group. You have to protect the aldehyde so you can use your Grignard on your ketone, and then once that chemistry is done, regenerate your aldehyde. So this is classic protecting group chemistry. The protecting group used is a cyclic acetal. So diol and acid used first protects your aldehyde. Grignard then attacks your ketone. Third step, protonation not only protonates your epoxide, but also deprotects your cyclic acetal, regenerating your aldehyde. So again, when and when not to use protecting groups is all based on relative reactivity. And that relative reactivity is aldehydes are more reactive than ketones. So hopefully that's just given you a little bit of an insight in how you should approach answering these exam questions.